We have developed a technology based on diamond for generating ozonated water on the spot for portable units, like the one unit over here. So the nice thing about this technology is really you can have portable units you can take around through the facility or whatever you need. It can be tank-based, meaning you can put water in it, or it can be just portable, smaller units. It can be, placed in the point of use through your facility. So, but the point here is actually to demonstrate kind of the efficacy of ozone in killing bacteria. And I was asked to demonstrate on the spot, to show how it does that. It's not that obvious unless actually you have technologies like these where we're going to use ATP. Anybody familiar with ATP measurements? 1, 2, 3? Okay. Just very fast. ATP is a molecule, adenine triphosphate, that is present in every single living cell. So bacteria and you all have any ATP. So it's actually used often in factories and environment, kind of public places to test for cleanliness. So you might actually find kind of sticks like this, maybe with a swab at the end that you can swab the surface and then test it with a device to show that the surface is clean. We're going to use here today, though, two different systems, kind of where you're going to dip it. We're going to dip this thing into the water, and we're going to measure how much ATP is in the water. Now, we're going to do it two measurements. One is going to be the total ATP, meaning whatever is free floating in the water from whatever, and as well how much is ATP inside the cells. Then we're going to take another measurement, which is going to be the free ATP only, and the difference is going to give you the bio load, meaning how much ATP is actually present in living cells. So the living cell system that we decided to use is not dangerous. I didn't want to bring Legionella here and then everybody kind of suit up with respirators and stuff. But we just thought about using probiotics. There's bacteria in here, large amount, clean and lyophilized, so it's very handy to have. There's nothing else in here, just kind of lyophilized bacteria. So what I'm going to do, I'm going to just take kind of one of this packet and I'm going to dissolve it into just clean water. And this is going to be my working solution. After that, I have two systems here. One is going to be treated with ozone, and the other one is just not going to be with the ozone, is going to be just filled up with just clean water. And we're going to see the difference between having ozone treatment versus no ozone treatment using the ATP to determine kind of the bio load. So there we go. And Jen here is going to help me with the aspect of the pipetting and measurements. So, okay. There we are. All right, it's gonna smell a little bit like yeast, so think about it. Kind of this will be the amount that you probably eat in one drink. So nothing dangerous. We have a lot of here. In here, we're actually going to have 200 CFUs, culture forming units. So here, then we have a 2 liters, and we're going to dissolve, we're going to take only 5 milliliters of this into these 2 containers of 2 liters, or 1 liter each. The final concentration in here is going to be about 500,000 CFU per mil. Just to give you an idea of what it means, by EPA, water cannot contain more than 1 CFU per 100 mil of E. coli. So that's kind of the highest limit. Here we're going to have an equivalent of 15 million CFU per 100 mils, which means we have 50 million times more, making the assumption that this is actually can be a dangerous bacteria. We're going to have 50 million times more bacteria than the limit that EPA is required for the E. coli. So, so we can start with the Meantime, actually running a little bit the system because the hose is pretty long, so I want to make sure it actually is purged by all the water that doesn't contain ozone, so they will actually have ozonated water as soon as actually I dispense it. $5 mil, right? Just 5. Okay. Oh, not yet. Oh, sure, go ahead. Okay, so now we're going to take this one, and we're going to just treat it with clean water. And so the amount here now is 5 million CFUs per 100 mils. Get a good shake so it kind of is nicely uniform. You don't see much. You see anything at all, in fact. Just clean water to the look, but there's bacteria inside. And now we're going to do the test of ATP with this. Huh? This it's just kind of same amount, just to make sure that actually it doesn't stick to the glass. So now here I'm going to actually fill it up with ozone. Meantime, Jen is going to measure it. And are you guys familiar with the smell of ozone? Well, maybe later, kind of when we're done with this, we can actually smell it. It's actually kind of pleasant as a relatively pleasant smell, like what you would expect kind of after a thunderstorm when the air is ionized. So we're going to add the water, ozonated water to the bacteria, and the ozone will kill it by essentially oxidizing the membrane of the cell, opening it, and like you would do with a raw egg, essentially, kind of open the egg and spilling out the guts of it. So we're going to put it at the same amount as we did with the other one.
So the total ATP on this one was 1188.
Oh, yeah.
Free on this one too, really.
Mm-hmm.
Thanks.
So the number here is RLU, relative light units. It's just a number from the chemical reaction that's happening there, which is a photoluminescence reaction. So it kind of generates light that the sensor can detect, and it's proportional to the amount. Okay.
So the live ATP is 540. I'm sorry, the free.
Right, so we have a total of 1,100, or 1,200 about, ATP for the total, living and non-living. The free, only the one is floating around among the living cells, is 540, which means there's a difference. 648 is actual living inside a living cell. Now we're going to do the same measurement, but with the water that's been treated with ozone, and hopefully demonstrating that ozone has killed the bacteria, and the ATP total will be equivalent or very close to ATP free, meaning that all the ATP now is out of the cell because the cell has been killed.
So this one has 838. So it's already gone down a little bit.
So the two numbers are relative numbers to each other, which means that now we only have 57 relative units compared to, before we had kind of 648 as a bio load. Now we have 57 as a bio load. Now the difference between these two is subtracted by that will give you kind of the kill rate of the ozone. So 648 minus 57 divided by 648. It's a 91% kill. So 5 million CFUs per 100 mils, kind of 5 million times more than what actually could be E. coli contaminated water, has a 91% kill bacteria. Any questions?
Will it continue to kill as it sits there?
To the extent that the ozone persists, it does. Ozone, however, in water has a relatively short lifetime, has a 20 minutes lifetime, so it will decay naturally. That's the nice thing about ozone because it's not like a persistent chemical, so it won't go down the drain, won't kill anything. Once actually it's in contact with the bacteria or the organic, it will react and then it's gone. So that's a nice thing. And eventually, technically speaking, like actually to drink this water is just DI water and kill bacteria and ozone that is gone by now. So it's totally kind of 100% environmentally friendly, green, and absolutely no chemical. The nice thing about ozone, I don't know if actually you mentioned that in your talk, is that it has a much greater range of activity than normal chemical like chlorine or quaternary amines. They have their own efficacy on different type of bacteria. For instance, chlorine might not be very effective on cryptosporidium, which is very common in water contaminations. But because cryptosporidium is a typical chlorine-resistant bacteria, ozone would actually kill it very efficiently. Quaternary amines they tend to be very used in food industry because they don't stink like chlorine. However, they have a little bit of a disadvantage. They are not very efficient against gram-negative bacteria. Gram-negative bacteria are Legionella, E. coli, Salmonella, all the kind of bad ones, essentially. And you end up having to use 4 to 10 times much more concentration than what actually is on the label prescribed by the manufacturer. Another kind of side effect of quaternary amines and other kind of chemicals that actually are not oxidants. So chlorine is an oxidant, meaning it actually kills it. Ozone is an oxidant, kind of opens up the cell. But non-oxidative disinfectants tend to actually just kind of stick to the cell and then prevent the cell to duplicate and grow, right? That will prevent them, they say, to form the biofilm. And then you can actually have other processes to remove it. However, when actually you interfere with the cell living mechanism, the cell can actually develop a way to go around it and develop resistance. So you might have heard about antibiotic resistance, right? That's actually when MRSA, that you actually get it, kind of, but antibiotic is not efficient anymore because the bacteria has developed that mechanism to circumvent that interference. Same thing with all the kind of other, there are some antibacterial soaps. They actually have another chemical inside. I don't remember which name is anymore, but it's been banned by the EPA because it can cause antibacterial resistance, and even more, it can induce the bacteria that you rinse off, in the sink, to develop even resistance to antibiotics itself. So, like Mike said earlier, there's the right chemical for the right application. So they can actually probably give you a good advice on where to apply the right chemicals or not, or where. Ozone is definitely kind of it's a green solution and has a greater efficacy to kill the bacteria throughout the facility. The nice thing about it, nice thing. Unfortunately, you cannot put it in a bottle and walk around with it and just apply it because it doesn't last that long. But the nice thing is actually you can have a technology like these that you can put in the place you need it. So you can have it by the faucet, or you can actually have a box kind of where you know that you have to kind of rinse something out. The foot rinse, and say kind of there's this kind of platform where actually there's the water coming out there. Actually, you can rinse your feet kind of going from one area to the other. You can think about having a box there that actually has ozonated water that sanitizes your feet and the platform itself, because by so you mitigate the cross-contamination across the plant. There's a variety of possible configurations for the ozone. So if you have other questions, I'm free to take them. Your cards, if you need my contact info, I will delighted to actually send you more information you need about this type of technology, and about ATP tests if you need anything else. Definitely Jen here can answer those questions as well. That's all.
Great, thank you.
Thank you.